Thanks. So I'm going to talk about structural learning of continuous models. And the motivation for my work comes from the real world. So many of the domains around us are continuous, right? A few examples that we'll see later is the chemical content of wine or census data or stock market, all continuous, and we usually treat them as discrete. Also, the structure of those domains is usually complex, right? So if we try to build a Bayesian network, for example, we expect a complex structure, and learning that structure is considered a relatively difficult task. We usually know how to do that for maybe 10 or 20, 30 variables. We want to scale that up and do everything in a much faster way. And the distribution of those domains is usually far from Gaussian, right? So as soon as we go into the continuous domains, we know the multivariate Gaussian, that's easy to compute, we'll meet it again. But when we try to be something more complex than that, everything slows down dramatically. So our goal is going to be to learn complex structure distributions and do it in a lightning speed way. Okay, so let's think about learning, and specifically learning of directed graphical models. So we're used to the axis of parameter estimation versus structural learning, and there's also the axis in terms of running time of model complexity. So at the top I have the linear Gaussian, which is the simplest parameterization of a continuous Bayesian network. And at the bottom, one of many nonlinear or multimodal distributions. And if we think of running time, we have this upper corner that we'll like to be in. The linear Gaussian, just parameter estimation, that's easy. That's basically the cheetah of continuous models, very fast. And if we want to do structural learning with that, we're still fine. We take n variables, we have approximately n squared edges, and we can still handle n squared cheetahs, right? But what happens if we want to be non-Gaussian? And that's the real world, right? The real world is far from Gaussian. Then even just with parameter estimation, we're stuck with basically a snail. No matter what the parameterization is, almost, right? The sigmoid parameterization, a mixture of Gaussian, everything slows down dramatically. Now we want to be, of course, in that corner, right? So we have to do n squared times snail, and that's really bad. And that's why structural learning is often just infeasible for larger domains. So if you talk to structural learning people, continuous domains, non-Gaussian, they'll say structural learning of 100 variables, near impossible. Okay, and we'll see that happening in a few minutes here. Okay, so imagine a world where I take that snail and turn it into a cheetah. And this is the work that I'm going to talk about today. Okay, we'll see that happening in real life. Okay. So how is it going to be done? So I'm going to give some background on Copulas. I know that many people haven't heard about Copulas before. And then I'm going to talk about a graphical model representation that uses Copulas. And that representation is going to give rise to this speedy procedure that is possible. So this procedure is only possible because of that construction. And basically the way that it works is that we're going to develop an efficient proxy to the model selection score. And that proxy is going to be so fast to compute that it's going to solve all our problems and transform the cheetah, the snail to the cheetah. I'm then going to present some theoretical and simulation results and some experiment on real-life data, and then I'll summarize. Okay, so what are Copulas? So technically, Copulas are a very simple construction. So let's say we have n variables, u1 through un, and these are continuous random variables that are uniform between 0 and 1. It's a very limited random variable. A Copula function is a fancy name for a joint distribution or joint cumulative distribution over these variables. So the probability that u1 is smaller than some value through un smaller than some value. Okay, so there is a fancy name, but this doesn't sound like anything that would interest us, right? Most variables are not uniform in 0, 1, not even marginally. So here's why Copulas are important. Let's say we choose any random variable xi and we look at the cumulative distribution of that variable. That cumulative distribution, regardless of what the original variable was, whether it was multimodal, Gaussian, or anything else, is uniform in 0, 1. Okay, that's probability 101, even if you don't remember it. And now we can plug that into any Copula function, and what we get is, voila, a joint distribution, a valid one. Okay, so construction-wise, Copulas are important because we can take any univariate marginals, plug them into the Copula. That's why they're called Copulas. They couple the univariate distributions, and out we get a joint distribution. Now, of course, this seems too magical, right? So the obvious question is, how powerful is this flexibility? So theory-wise, there is a theorem by Sklar that says that any joint distribution can be represented by some Copula function, but that doesn't help us, some Copula function. So let's see an example of how strong a very simple Copula function is. Okay, so this is what's called the Gaussian Copula function, and the Gaussian Copula function takes the cumulative distribution function of x1 through xn. So remember, these are variables that are marginally uniform in 0, 1 always. We pass those through a standard inverse Gaussian. Okay, this is just part of the representation, and then we put a Gaussian over the entire thing. Okay, so it doesn't matter where this strange function came from. It's a simple Gaussian parameterization, but now the Gaussian is over some transformation of the univariate potentials. Okay, now let's see how strong even this simple parameterization can be. So let's say that I take Gaussian univariate marginals. Now, if this is Gaussian, then after I invert it using an inverse Gaussian, it will stay Gaussian. And if I put a Gaussian on top of all of that, you can already guess that what I'll get is a joint Gaussian distribution, right? And I'm not here to tell you how to construct Gaussian distributions. That's easy. But now let's take the same couple of functions. So still this function. But now instead of f1, x1, and f2, x2 that are Gaussian, let's take one that is Gaussian and one that is a gamma distribution. So the dependence function is the same, that function that couples the univariate distributions, but the univariate distribution is different. And now we get a joint density, a bivariate density in this case, that is very different from Gaussian distribution. Okay, if you saw this, you would never imagine it arises from a Gaussian dependence. And we can take this one step further. So now I take an exponential marginal, a multimodal marginal, and what I get is something that starts to look like a complex bivariate distribution, right? And remember, all that I did was change the univariate marginals. And those are very easy to change, right? Because univariate estimation is very easy. So this is the power of copulas. You can take basically any univariate marginals, any Copula function, and you get a recipe for constructing multivariate distributions. And in the last 10 or 20 years, there has been an exponential increase of applications, and lately Copulas have even been blamed for the fall of Wall Street. Probably not true, but, well, it's true that they've been blamed for it, but probably not the functions are to fault. And it might seem, okay, the problem is solved, right? We have a mechanism for constructing complex multivariate distributions. The only problem is that in practice, copulas are only good for a few dimensions. Okay, they work well for 2, 3, 4 dimensions. Sometimes you see applications with 7 dimensions, but never more than that, right? And in machine learning, we want to think graphical models, so we want to somehow enlarge that. And this is where the Copula network model comes in. So the Copula network model basically fuses the Bayesian network formalism and the Copula framework. So we have a graph. This is just a Bayesian network graph that you all know that encodes independencies. We have a set of local Copula functions. So instead of local conditional distributions, what we have are local Copula functions, and small c here is a Copula density, just the derivative of the Copula function, over the marginal of xi and the marginal of the parent of xi. So far it still looks like a Bayesian network. And now comes the new component. We have an explicit representation of the univariate marginals, okay, or in this case densities. And given all of this, it turns out that just like we construct joint distributions in Bayesian networks via composition, we can also do this here using copulas. And the theorem from a year and a half ago says that we can construct a valid joint density over all variables via a product, so a product over variables in this graph, of the univariate marginal density of each variable times the term. The tilde here just means it's a term. It's not exactly the copula that depends on the local copula. Okay. So what's unique about this construction and is different than regular Bayesian networks is that this construction, actually the marginals of this entire distribution are exactly the ones that we put in. So we somehow get control over the marginals. And it turns out that that control over the marginals buys us a lot of ground in terms of log probability on test data. And we'll see that as we go on. Okay, so we have this construction. And now, just like Bayesian network, we want to learn the structure of that construction, right? And it seems like everything here is a bit more complicated. There are the univariate marginals, there are those weird Copula functions, and somehow it seems that learning will be slow. And what we'll see is that we'll actually compete with a cheetah. Okay, so how do we do structural learning in general, both for Bayesian networks and Copula networks? We have data, we want to output some graph. We usually start with some initial structure. It can be an empty structure or a tree structure. We look at neighboring structure, let's say using addition and deletion of edges or something like that. We score each of the candidate structures, right? And then we choose the best one and so on. And of course, there are lots of variants on this algorithm, but generally this is a very common algorithm for learning the structure. Now, note that in order to do this, what's costly is the computation of the score. We'll talk about that score in a second. And that score is usually something like likelihood minus penalty on the complexity of the model. But we don't actually need to compute a score in order to do this. What we need is just a ranking of the score. Right? If we could say this model is better than this and better than this, we don't really need the actual score. And this is exactly the surrogate that I'll give in this talk. I'll give a proxy to the model selection score that is monotonic in the score in some sense. You'll see in a second how. And that will allow us to learn the model very quickly. Okay, so I've said this. So let's look at the surrogate for the score. So if we just look at a single edge for now, from x to y, the contribution to the score of that edge is simply the sum over instances, m instances, of log the Copula density term. And remember, the tilde is just a term. I didn't show the explicit details, but you can think of it as the Copula density. And that Copula density is over the marginal of x in the mth instance and the marginal of y in the mth instance. And remember that the distribution of this is always uniform. So everything here is plugged in the right place. Okay, so what's difficult here? I mean, computation of the density is not difficult, but computation of the maximum likelihood parameters is difficult, and this is what takes time when we do structural learning. Okay, so an idea is maybe use the Copula entropy as a proxy to the likelihood. And this idea comes from an asymptotic view that says that as m grows to infinity, as the number of samples grow, right, this term just goes to basically this integral, which is just a negative Copula entropy. Okay. So it sounds nice in terms of asymptotics, but it doesn't bias anything. Okay, computing this integral for most Copulas is just as difficult as computing the likelihood. But this is what we're going to do. We're going to find a surrogate for this entropy, and this surrogate is going to be the proxy to our model selection score. Okay, and now we get to the surrogate itself. So we're going to use Spearman's rho. For those who haven't heard or forgot about Spearman rho's, it's just a non-parametric measure of dependence between two variables. So there's supposed to be x and y here. Okay? So let's say we use u to denote the cumulative distribution of x and v to denote the cumulative distribution of fv. Okay, so these are, so over the distribution, these are simply the cumulative distribution or the ranks if you think about the empirical version of Spearman rho. And then Spearman rho is simply the Pearson correlation, but instead over the original variable, over u and v. Okay, so just the covariance over u and v over the standard deviation. Okay, this is Spearman's rho. Spearman's rho, if you sit down and play with it a bit, you'll see that it equals 1, for example, when x and y have a monotonic relationship, a perfect one. It equals -1 when they have a negative monotonic relationship, and so on. So in some ways, it captures the dependence property between x and y. Okay, how is this related to Copula? So it turns out, and this is actually just a two-line proof, that Spearman's rho is intimately connected with Copula. It equals to, forget the coefficients here, it's proportional to the integral of the Copula function. And this is quite easy to prove. So there is a monotonic relationship between the Copula function and Spearman rho. Okay, it's still not between the entropy and Spearman rho, but this is the fact one that we're going to use. The second fact is that most Copula functions are monotone with respect to theta as their parameter. So even the Gaussian Copula that I showed before, if you think about the off-diagonal parameter, the Copula itself is monotone in that parameter. And that's true for the vast majority of Copula families. In fact, they're constructed that way, so that when you raise the parameter, the dependence would be stronger. And if we use those two facts, we already have the Spearman rho is monotone usually in the parameter. That still doesn't mean monotone in the entropy, but it's a start. Okay, so let's use that, and I'll just show the theorem. I won't give the proof, but just the essence of the proof. And the proofs are very simple. It's more the insight that this could happen. So the first theorem is that the absolute value of Spearman rho, and we need absolute value here because of positive and negative dependence, is monotone in the negative entropy of the Copula for the Gaussian NT Copulas. And this is basically proven by, there is a known relationship between rho, Spearman rho, and theta. We take that and we compute an explicit form of the entropy. This is possible for the Gaussian distribution or also for the Gaussian Copula. We plug those two together, do some algebraic manipulation, and we get the result. The second theorem in the paper says that absolute value of Spearman's rho is monotone in the negative entropy for the Fairley-Gumbel-Morgenstern Copula. Now I doubt that anyone here has met it, or maybe a couple of people, but it's a very common copula, mostly because it has a simple analytic form. And to prove that result, we basically use the closure under convexity of the family and the property that we talked about before, the monotonicity with respect to the parameter. Okay, so what do we have now? For three actually, very popular copula families, the Gaussian copula is by far the most popular, we have a theorem that says the Spearman's rho is monotone in the negative entropy. Now the obvious question is whether this holds for additional families. So I can't give you a theoretical answer, but I can give you a simulation answer for some families. So we did simulation on additional families. So we chose 500 parameter values, 25,000 samples, and I'm going to show you the result for the Clayton copula. And if you see on the y-axis the expected log likelihood, on the x-axis the absolute value of Spearman rho, I mean this is clearly monotone, right? It's not a theorem, but it's very clear that we just have to find a way on how to prove this. And it turns out that this is actually true for many other copula families. In fact, all copula families for which I could find code that someone wrote or that I myself completed. So we have some general property here. We only proved that property for 3 families. And it's actually a theoretical challenge that I'm working on these days on how to actually set general conditions for which this is true. But this certainly holds for many families. Okay, so now how do we do structural learning with that? Very simple. For trees, we just have pairs, right? So we compute the empirical Spearman rho for each pair of variables, and we find the optimal tree just like doing a child-root tree for regular Bayesian networks. And this is actually, if the data is generated by a copula, this is actually asymptotically exact. And if we go beyond trees, for single parent families, this is still exact if the data is generated for copulas. For multiple parent families, we just use a standard heuristic where we crudely use Spearman rho to rank candidates, and then we apply the snail just to the few most promising families. Okay, so let's see how this at work. And I'm going to consider 3 data sets. A relatively small one with 12 variables of chemical properties of wine, a medium-sized one of 30 stocks from Dow Jones over 5 years, and a larger 100 variable one from the crime domain. Okay, and this is already pretty big in terms of structural learning, definitely in terms of copulas. And before showing the results, everything that we did was theory, asymptotically, in case the data came from a copula. The first question is does the approximation work well for real data? So let's look at the approximation for the crime data. It's more or less the same for the other ones. So what I'm showing here is the log likelihood per instance versus Pearson's correlation, so not yet Spearman. So you might say there is a relationship. Pearson is not that bad, but there are also lots of misses, especially in this area, right? So you get a lot of optimistic and pessimistic views of models, but if you now look at Spearman's rho, right, this looks almost like a perfect proxy to the mental selection score. So this is finite data that we don't know if it came from a copula or not. And basically the conclusion is that we can use, even in practice, Spearman rho as an accurate proxy to the model selection procedure. And now let's do just that. So we look at 10 random train test partitions. We consider models with different complexities, so from 1 parent, which is a tree model, to 4 parents altogether. And what we show here in this graph are all models for all 3 domains. So this is the wine domain, this is the Dow Jones domain, and this is the crime domain. The y-axis is our speedup factor, and the x-axis is the standard runtime of the copula Bayesian network without our trick. And what we see, for example, so tree models are obviously faster to learn than more complex models, and our benefit is greater because we don't have to use the heuristic. But even for complex models, if we look at this region, then what we have is something that takes around slightly less than 10 to the 4th seconds, but our procedure is 50 times faster. So this is quite significant. And what's really important is not only that the speedups are significant, but actually that they increase with the domain size. So if we now go to a bigger domain, we'll get even bigger increases. Okay, so we're told one there, okay, this is too good to be true. You're fast, but you're probably paying some price. So let's look at the approximation quality. So here we see the log loss per instance of standard learning versus log loss per instance using our method. I mean, these look right on top of each other. And here there is a small price to pay. So basically, there is no effective cost in small to medium domains, and there is a very small cost to accuracy in large domains. Okay, so now let's go back to the cheetah. Okay, when we compare to, so far we compared to learning Copula Bayesian network using standard procedure. But remember, the linear Gaussian was the cheetah that we like, right? It was very fast to learn. So now this is the linear Gaussian runtime. This is not a Copula network anymore. And this is the speedup factor of our procedure versus that cheetah. So for small domain, we're paying a small overhead. And for the larger domain, we're actually faster than the cheetah. Now this is, just to be fair, this can be brought down to 1 if we apply our same trick to the linear Gaussian learning. So we're actually as fast as the cheetah, not faster. Okay? And in terms of accuracy, and that's really important, like if you look both at the Wine, Dow, and Klein-Jones, the improvement in bit per instance is quite significant relative to the cheetah or the linear Gaussian Bayesian network. For the Klein domain, we get an improvement of over 10 bits per instance. So that means that each test instance on average is 2 to the times 10 more likely using the model. So what we have is a lightning speed procedure, but with substantial performance gains, and we're used to the fact that there is a trade-off between those two. And at least that construction gives us rise to a regime where we won't have that trade-off, or have it just in a little way. Okay, so to summarize, basically we showed that expected log likelihood is monotonic in Spearman row. We proved that for 3 families and showed via simulation that it's true for many others. That led us to use Spearman row as a proxy to the model selection score. So we do structural learning with Spearman row, and only on the final model actually do costly parameter estimation. Basically, we turn the snail into a cheetah, and now we can do lightning speed structural learning of complex networks. Thank you very much.
Great talk. The improvement that you get over the Gaussian cheetah in terms of predictive performance, is that because it can find better structures, or is that because it's modeling the marginal much better?
I think it's because it's modeling the marginals much better. And I mean, that's true generally of Copula models. Because you capture the marginals so well, you need simpler dependence functions in order to get a great joint distribution.
So I guess I'm interested in what is the fundamental difference between what you're doing and the process of Gaussianizing all the real valued data to start with, and you're just using standard techniques in terms of development of Bayesian networks and conditioning models in that setting.
Right. So
there's a lot of similarity.
There is a similarity, and I don't have the graph here, but I actually tried it as an early experiment. It doesn't work nearly as well, and the reason is that I'm actually not changing the distribution of each variable. I'm just looking at the cumulative distribution instead of the values themselves. And that's definitely not Gaussian. So I'm actually keeping the original distribution intact. So if the original distribution was multimodal, and it is for some variables in the crime domain, it is still multimodal in my domain. So in the original paper of the framework, you can actually see distributions that are very non-Gaussian in my model. And
but those are the distributions that you're conditioning on. So you're conditioning on those.
Right. But those are also estimated from real data. So if the data originally were near Gaussian, none of this would be needed, of course.
I can only take one more question.
So this is probably a bit simple, but I'm just wondering how the class of systems that you can model with a Bayesian network compares to how the class of systems that you can model with copulas, and are they approximately the same size? Are they the same set of things, or is one bigger than that?
Okay, so there's a gap here between what you can do in theory and what you can do in practice, right? Bayesian network can accept any conditional distribution, but in practice we're limited to very few forms. Now, the Copula theorem, the main Copula theorem from 1959, says that any joint distribution can be represented using Copula, where you plug in just the true marginals into that Copula. So in that sense, Copulas are very powerful. In the practical sense, Copulas are powerful because it turns out that it's easier to construct distribution over the 0-1 grid than the general grid. So there are probably 10 to 30 very common Copulas and a lot more less known Copulas. And that's a lot more joint distributions than we're all used to, right? I knew about 3 joint distributions until a year and a half ago. So that definitely expands the bank of distributions that we can work with.
Thank you very much.